Good afternoon, everybody. Thanks to the TCT for the opportunity to come here this afternoon. I've been with BAE now since 1981 in a variety of roles. At the start of this year, I was actually privileged to be asked to head up the Agile Product Development Centre. And that's really aimed at how we're going to discharge some of our future aircraft programmes, looking at the emerging technologies that need to be put in place to meet some of the challenges that I'll talk about in a couple of minutes' time. And really, this is about how do we set up a facility up where we're going to do low-rate volume manufacture, development products, demonstrator products, away from sort of the mainstream production systems that we currently have running at our Samlesbury and Wharton sites. Because what typically happens is you bring a new development program along, it starts to fail because the mainstream production programs, which are the current cash cows, stop the work being progressed through the factory whilst we're maintaining the here and now. So a lot of focus on how do we set something up that's flexible, agile, very responsive, but also enables sort of the demonstration of end-to-end processes. And again, as we look at sort of the additive manufacturing activities, there's typically some specialist people who've got intrinsic knowledge that they carry around in their own heads in terms of the processes. Part of the role that I've got is to how do we translate that through into a mainstream production system that can be deployed by the broader population as we track forward. So taking on the challenge of the new facility, I was given the task 50% out of lead time, 50% out of cost. I should have walked away, but I didn't. So we'll crack on. First phase of the facility is actually standing or consolidating our additive manufacturing capabilities that we have that are currently distributed around a number of our sites within military air. So what I want to do this afternoon is really give you an overview of what we see as the art of the possible with additive manufacturing, where we are today, and probably equally as important, some of the challenges that we face as we move this process forward. Make no bones about it, there are some real challenges there that we still face in terms of taking additive manufacturing into flying products. So just for familiarity, military air, we produce a number of products. We've got the Hawk aircraft, been around since early 1970s in its current guise. Typically, we've sold over 1,000 of these products. Typically, we're now into sort of export opportunities with them, relatively small batch, reasonable high degree of customizations associated with them, particularly around the cockpits, which we can configure to meet any of the sort of military aircraft programs that are currently flying around the world. So again, how do we become responsive to the demands of what are relatively short volume orders for these products? Typhoon, people are probably very familiar with that, projected to manufacture at the moment, 719, coming towards the end of the partner nation buy of 620. So again, we're moving out of a mainstream production environment into one of export orders, which will be relatively short, challenging timescales from customers in terms of lead time to market, and levels of customization to meet the requirements of the export customer themselves. F-35 went into production in 2004. We're responsible for the back end of the aircraft in terms of the rear fuse, vertical tails, horizontal tails. Again, that will probably predominantly be the mainstream rate production program that we see going through our factories for the next 20 years, subject to us being able to maintain the affordability challenges that are being placed on us from our customer, who's Lockheed Martin. A couple of examples there of some of the demonstrators that we've produced recently in terms of preparing ourselves for our future aircraft programs. So you've got the Mantis, Tyrannus, remotely piloted air systems. Tyrannus came into sort of public domain beginning of this year, announced at Farnborough, through the trials that have been undertaken out in Australia. And again, demonstrator vehicles, there's likely to be a or hopefully there will be a further demonstrator vehicle in the not too distant future, where we need to be able to respond responsively to the requirements of that product. If you look at any product as we go forward, there are always the inevitable challenges, and they're no different from when we produced Hawks through F-35. They will be the same, albeit more exacting as we go forward in terms of how do we take the weight out of it, how do we make it go further, how do we increase its endurance, its life, because these things are typically subject to fatigue. How do we ensure that in service it doesn't cost the user lots of money to maintain the product, and then from an operator, how do we make sure he can't be seen and comes back safely in terms of the nature of the product. And typically with these things, the more you invest in those or implement those activities, the greater the cost goes. The real dichotomy there is that the customer's budgets are actually going in the opposite direction in terms of availability to fund these products. So really our challenge is how do we give them more for less as we track forward. To do that, we're looking at a whole series of disruptive technologies. The ones that you can see here are typically what I would consider to be additive technologies. Fibre placement around the fuselage structure there. So there we're laying down tows of carbon fibre material, number of different orientations, building up the product. So carbon fibre additive manufacturing has been around in our industry since the early 80s from a production perspective. Similarly, laying up of the carbon skins, struts, spars and ribs in terms of a bonded structure, doing away with fasteners, saving lots of money in terms of the assembly costs. And then we've got probably what people would consider to be the more traditional or AM activities in terms of the hinge arrangements that you can see in the top right-hand corner, and the lower left-hand corner, the introduction using additive manufacturing of mechanisms and systems integral to component parts, which the printing type processes lend themselves to quite readily. And then taking a projection further forward, a whole series of concepts. Some would consider it science fiction, and I think time will tell as to whether that is the case. But there's some examples there in terms of the scary activities that the concept designers and boffins within our future engineering systems are coming up with in terms of aircraft, which can combine to enable long endurance flights, separating to provide different mission capabilities at points of deployment, whether that's command and control, strike, air defence type capabilities, all of which start to envisage new technologies being required to enable those activities. Right hand corner there you can see the ability to self-heal skins and substructure, the use of energy systems to direct and take out missiles as part of an air defence capability, and towards the back end there you can see potential 3D printing of aircraft. I'll start video here, but again the principle here is that we have a large aircraft providing a mission in a disaster area at this point in time, looking for survivors. The aircraft has a 3D printing capability on board it to, in effect, create a small unmanned air vehicle that can go and do close surveillance of the area, identify a potential person that needs pulling out of that situation, and then creating another vehicle that goes and deploys him. I'm sure I've seen that picture on that model on the Stratis stand at the front of the office. But could be science fiction, but a lot of the enablers are starting to be put in place as incremental solutions. The real challenge over the next few years is about how do we take those, integrate them, build them into a product that we can then certify for flight going forward. Within the actual marketplace itself, the economic environment, there's some other real pressures that not just our business, but the aerospace business, probably business in general within the UK faces. Affordability challenges, the dilution of capability, the loss of technology out of the environment to other countries, other economies, challenge of through life costs, how do we exploit our IPR, globalization. With export opportunities comes usually the demand for in-country industrialization activities. And with these countries, they're always looking for that, what's the next step in technology. So, if we don't develop and have the ability to discharge those technologies into other nations, then we kind of lose the opportunity to gain the export potential. Environmental conditions, we've got REACH processes, etc., all of which are trying to divide more environmentally friendly processes to be utilised. And you can see some of the challenging nations that we've got there in terms of Brazil, China, etc., who are sort of the forefront of the next round of technological nations, and then the lower cost economies of Brazil, Mexico, Turkey, Indonesia, etc. All snapping at our heels. So the real challenge there is, how do we take costs out? How do we improve or sustain the environment that we live in? And certainly I believe that some of the additive manufacturing processes have got a role to play in the majority of those issues as we go forward. And you can see there, from a coming down to military aerospace, the real challenges that we face are reduced large production runs. The UK government is no longer in a position to support the manufacture of large volumes of aircraft. He's looking for bespoke, low volume solutions. Strong affordability challenges, need to implement things into the export marketplace. So where does additive manufacturing fit in that? You can see there that we're currently really looking at 5 key process areas: stereolithography, fused deposition modelling, SLS, the sintered laser solution, in the non-metallic areas. And then from a metallics point of view, we're looking at large tie deposition techniques in terms of building primary load-bearing structures, and the sintered laser melt techniques, the powder metallics, around some of the secondary structures. So stereolithography has been around in our business since the early 90s. Primarily started off as a visualization technique, and that is still very important to us even to today. Whilst we are in a 3D CATIA solid modelling environment, the ability to produce and physically examine how parts can go together and some of the assembly issues are still quite difficult when you're on a CAD box. So there are lots of usages there for that application. More latterly, with the introduction of some of the bluestone, greystone resin systems, we've actually been in a position whereby we can manufacture rapidly bespoke tooling for assembly applications, typically around sort of drill blocks, setting tools, etc., where there's a high degree of customization, bespokeness of fitting of brackets and things like that into the aircraft. So there's some real good uses of that process there, with demonstrated accuracies being available to us. Fused deposition modelling, primarily there we're looking at sort of the ABS and the nylon Ultems material. From an ABS point of view, a lot of that's evolved around covers, transportation media, where we've been able to take significant cost either out of the media in supporting transportation, out of the cable support tool that you can see there, or from a covers perspective in service, being able to protect components in an efficient operator manner whilst the aircraft's being serviced. And the example that you can see in there in terms of the service shaft protector has saved us several million pounds being projected forward across the the RAF's fleet of aircraft in terms of damage that inherently could have occurred to the product it's supporting. And more latterly, we've actually started now to develop the wherewithal to produce form tools that enable us to form sheet metal components for a relatively short run of component manufacturing requirements using some of the high intensity presses that we have in place in the factory. So again, starting to give us that flexibility to produce quick turnaround tooling that's suitable for low volume manufacture. Where we're moving to now is around the use of the ULTEMS material in terms of qualifying that material for use in what I would call medium temperature air cooling ducts, and we're going through a qualification life cycle on that material at this point in time. Similarly, the SLS process, the example there again, we see a lot of applications for this in terms of complex, lower temperature cooling systems on the aircraft. And the example you can see there is a cooling duct for a new radar that's been introduced. In going down that route, we had to improve the performance characteristics of the cooling duct over and above the existing duct that's in place, and we exceeded the expectations in that area. We mitigated the requirement for new tooling. Through the process, we unitized the structure, so we took costs out in terms of combining 7 components down to 1 component, and the product was lighter. All real positives in terms of how we move the aircraft forward. Moving into the metallics, SLM process, we're really in a development phase on this at this point in time, trying to explore what the capabilities of the process are and how the best mechanisms for deploying those capabilities. A couple of examples there of camera brackets that have flown, both on Tornado and the Taranis product. Again, process lent itself to a quick turn in terms of being able to design and manufacture the brackets very quickly to enable observation of some of the development flying requirements on both of the products. But really, just replicating a standard bracket doesn't really give you the maximum benefits that this process affords. Where you really need to go to is more of the topographically designed parts, i.e. where materials being placed where the structural loads demand it. And the example you can see there is the Tornado bracket being replicated through topographical design, and we saw 60% mass reduction from what will be a standard design through to the topographical design. So moving forward, subject to us to being able to qualify materials and the process, we can see some significant advantage in that area. Probably the last area that we're really focused on at the moment is large titanium structural components. Some examples there of demonstrator spars that we've produced either through laser blown powder deposition techniques and one that's been produced through wire plasma arc deposition techniques. Again, demonstrating the performance characteristics of the process, the material properties that we achieve, and we're currently cutting those samples up and validating the characteristics of those components. But for me, this is potentially one of the real critical areas going forward, in that with the low volume manufacturing rates, these products would typically have been forged on some of the larger programs that we've got. We now no longer are going to have that leverage within the supply chain when you recognise that the Airbuses and the Boeings of this world are producing 60, 80 aircraft sets a month. They're going to be placing work into the same forging houses. Are we going to have the opportunity to have any leverage with those houses as we track forward? So these techniques, I believe, are going to be invaluable in terms of the low volume requirements as we track forward. So I guess the question is it all rosy in the garden? Well, the answer to that, probably not at this point in time. there's still some challenges with all of those processes that we face going forward, and that we're working with at the moment to address those challenges. I guess the least challenged one is the stereolithography. Probably the key question we've still got there, even with some of the tooling that we're produced in, is what's the levity of those tools. We've seen a level of degradation through exposure to UV light. How long do they last for? And I guess, you know, one of the challenges back to the supply chain is, are the new resin systems coming through that can, whilst meet the tolerancing and accuracy requirements, demonstrate superior handling and life qualities. FDM, and starts to become a bit of a consistent theme, is the quality assurance that we can gain through the supply chain. We've got to have some real consistency of material standards and sources of supply, and proof of that or assurance of that supply chain, critical to anything that we put on our aircraft. Similarly, validation of the actual process capabilities. There's not a lot of definition there from the supply chain, from the manufacturers, in terms of over the size volumes that are available to us, how accurate can you produce a part, what degrees of shrinkage, what performance characteristics have they built into their machine controllers to accommodate the various material types that are being offered into the marketplace. So some considerable work there for enable us to design with those materials in mind. Surface definition, particularly with FDM, because you're laying stratas, you get a step surface, particularly on curves. How we address smoothness of those activities, and generally the process speed that we see with this process is somewhat challenging. SLS, again, same issues around the supply chain and verification of the process capabilities. Further issues being a powder technology that a percentage of the powder doesn't get consumed during the manufacturing process. What do we do? How do we reuse it? What's the degree of recirculation that can be undertaken on those materials? And again, there's not a lot of evidence out there in our applications to enable us to be able to say we've got a robust production solution at this point in time. Metallics, again, topographical design. It's about the tool set. Structural engineers who actually sign for the aircraft are by nature very conservative. They want to be really confident that the product that's produced matches the calculations and the loads being applied. So how do we get a tool set that takes a vision through to a finished component and understand that the output matches the inputs in terms of loads? And again, in that area, material reusage and issues around the effectiveness of the surface finish. Inherently, it tends to be a rough surface. It's got stress razors in there, and again, that starts to have implications back into the fatigue life and calculations that will be applied to those components. So some real challenge in terms of understanding those conditions and what they mean back into the design set. And for the large tie deposition activities, probably the key ones on there: distortion elimination, a lot of temperature, whether it's with lasers, plasma arc, resulting in distortion of the products. How do we define that, quantify it, build it into the design standards, and then how do we put a production system in place? And by a production system, that's the physical process understanding. It's about the machine or the physical system that discharges that process, and it's about the tool set that enables you to drive that process from a design through to a production engineering methodology. Lots of examples of this in academia. How do we translate that through into a production environment are some of the real challenges that we face. And probably the overarching challenge with a lot of this is how do we educate the engineering teams to select and design for the processes appropriately. You know, as I say, intrinsically this is left with a few experts within the business who try to evangelise the process. It's not a mainstream solution at this point in time. So in conclusion, I think there are some significant challenges that we're working through, and I believe we will crack those challenges. We've got to get supply chain standardisation and controls and maturity in place. Got to get some clear process capability, understanding established, documented, and being repeatable as we start to increase the rate and the volumes of the capabilities that we have. We've got to have the production systems in place. That's the end-to-end tool set, the physical capabilities to enable us to operate these things. They're fully documented, and as I say, it's an internal challenge in a lot of instances in terms of the processes and the guidelines that we need to put in place so that the general engineering population can operate with these capabilities. And then we've got to go through quite an intensive education process to ensure that there is an appropriate take-up and deployment of these processes as appropriate. Well, I think in going through all that, the conclusions I've come to in the last 9-10 months are that, subject to us cracking these issues, this set process, it's not going to be the panacea. I really don't believe that it will be the panacea. I think it can be a very powerful tool in the toolbox in terms of being able to move the business forward, the products forward, going forward, into the future. Printing aircraft, I guess the jury's out on that yet. We've got a ways to go to crack some of the basics, but possibly. And time will tell, in my opinion, as to whether that vision of printing an aircraft will come to reality. But certainly, even looking around the show today, there are aspects of things on the stands that you can say they are elements of that vision, and it's how we bring those together. Thank you.